Look up at the night sky. What you see, the pinpricks of light against a velvet darkness, is just the tiniest fraction of the story. Beyond those familiar stars and swirling galaxies lies a realm of pure mystery, a cosmic frontier where the rules of physics are stretched to their absolute limit. In that profound darkness, at distances so vast they defy human comprehension, lurk some of the universe's most enigmatic and powerful objects, supermassive black holes. But we're not talking about the well-known giants at the center of nearby galaxies. We are journeying to the edge of everything, to a time when the universe was in its infancy, to confront the most distant black holes ever detected. These aren't just cosmic curiosities, they are ancient behemoths, time capsules from the dawn of creation, and their very existence challenges everything we thought we knew about how our cosmos evolved. How is it even possible to see something that is, by its very nature, invisible? A black hole's gravity is so intense that not even light can escape its grasp. The answer lies not in the darkness itself, but in the furious, chaotic maelstrom that surrounds it. Imagine a whirlpool of superheated gas and dust spinning at nearly the speed of light before it plunges into the abyss. This process creates the brightest, most energetic phenomena in the entire universe, quasars. It is the brilliant, screaming light from these cosmic engines, traveling for billions of years across an ever-expanding void that finally reaches our telescopes. Each photon is a messenger from an ancient past, carrying with it secrets about the extreme conditions that shaped the early universe. Detecting them is one of the greatest technical achievements in human history, a testament to our relentless curiosity and ingenuity. In this video, we are embarking on an epic expedition to explore 50 incredible facts about these universe's most distant black holes. We will unravel how astronomers spot these needles in a cosmic haystack, piece together the puzzle of how they grew to such immense sizes so quickly after the Big Bang, and confront the profound mysteries they hold about the origins of everything, from the first galaxies to the very fabric of space and time. This is more than a list of facts. It's a journey to the farthest reaches of reality, a story written in gravity and light waiting for us to finally read it. So let's begin. To truly grasp the awe of these discoveries, we first have to wrap our minds around what distant actually means in the grand theater of the cosmos. It's a concept that goes far beyond simple geography. When astronomers talk about a black hole being, say, 13 billion light-years away, they are describing two incredible things at once. The first is an almost unimaginable physical distance. A single light-year is the distance a beam of light travels in one entire year, moving at the fastest speed possible in our universe, about 6 trillion miles. Multiply that by 13 billion, and you have a number so vast it loses all practical meaning to our human-scale brains. But the second and far more profound meaning is about time. Because light, while incredibly fast, still takes time to travel across these immense voids. When the light from that 13 billion light-year distant black hole finally reaches our telescopes, it has been on an epic journey for 13 billion years. We are not seeing the object as it is today, we are seeing it as it was when that light first began its voyage. We are peering directly into the past. This is the magic of look-back time, a form of cosmic time travel that is not science fiction but a fundamental tool of astronomy. That distant black hole we observe is a snapshot from an era when the universe itself was in its infancy, a mere 600 or 700 million years after the Big Bang. To put that into perspective, if the entire history of the universe were compressed into a single calendar year, the Big Bang would occur at the first second of January 1st. The formation of our own Sun and Earth wouldn't happen until early September, but the light from these most distant black holes is a message from the first few days of January, a glimpse into the universe's very first chapter. It shows us a cosmos that was radically different, smaller, hotter, denser, and filled with the raw ingredients for everything that would ever come to be. Now let's meet the current champion of cosmic distance, a quasar that holds the title of the most distant, and therefore the earliest supermassive black hole ever observed. Its name might sound like a serial code, J0313-1806, but it represents a frontier of discovery. This beacon from the dawn of time is located a staggering 13 billion light-years away from Earth. To put that into a human context, the light we are capturing from J0313-1806 today began its journey when our universe was only about 670 million years old, a mere 5% of its current age. We are witnessing an event that occurred before our own galaxy, the Milky Way, had fully taken shape. The discovery of such an object was a monumental feat of international collaboration and cutting-edge technology. It was pinpointed using the powerful Gemini North telescope atop Mauna Kea in Hawaii, which first identified its extraordinary redshift, a key indicator of immense distance. But the observations didn't stop there. The Atacama Large Millimeter/Submillimeter Array, or ALMA, a revolutionary collection of radio telescopes high in the Chilean desert, then turned its gaze toward this distant speck. ALMA's incredible sensitivity allowed astronomers to peer deeper, confirming the quasar's distance and even detecting the faint whisper of dust and heated gas swirling around the black hole itself. This 1-2 punch of optical and radio astronomy provided the ironclad evidence needed to crown J0313-1806 as the record holder. Yet the true shock wasn't just finding it, it was the sheer scale of the monster they found. The black hole powering this quasar is a supermassive leviathan, estimated to weigh in at over 1.5 billion times the mass of our Sun. And this is where the story becomes a profound puzzle for cosmologists. How does a black hole grow to be more massive than 1 billion suns in less than 700 million years? That's the cosmic equivalent of a baby growing to the size of a blue whale in just a few weeks. Our prevailing models of black hole formation suggest they start from the collapsed cores of the universe's first massive stars, stellar mass black holes that are perhaps a few dozen times the mass of our Sun. They then grow over billions of years by slowly consuming gas and merging with other black holes. But J0313-1806 completely shatters this gradualist timeline. There simply hasn't been enough time in the early universe for a small seed to balloon into such a colossal object through normal feeding processes. Its existence forces us to consider radical alternatives. Perhaps the first black holes were born big, from the direct collapse of enormous clouds of primordial gas, skipping the star stage entirely and providing a massive head start. Or maybe, in the dense, chaotic environment of the early cosmos, the rates of accretion of feeding were astronomically higher than anything we see in the modern universe. This single point of light, a message from the cosmic dark ages, is actively challenging our fundamental understanding of how the most powerful objects in the universe came to be. So we've established the staggering distances involved and encountered one of these ancient titans, but that leads us to a truly fascinating question. How do we actually see something that is, by definition, invisible? The answer lies not in the black hole itself, but in the cosmic tantrum it throws. When a supermassive black hole is actively feeding, it doesn't do so quietly. It becomes the engine for the most luminous and persistent objects in the entire cosmos, quasars. The process begins with an immense disk of superheated gas and dust spiraling inward at incredible speeds, a structure known as an accretion disk. As this material is pulled ever closer to the event horizon, the point of no return, it is subjected to unimaginable friction and gravitational forces, heating it to millions of degrees. This hot, frenzied maelstrom doesn't just glow, it shines with the brightness of 1 trillion stars, outshining the combined light of every single star in its host galaxy. This is the primary beacon that allows us to detect these objects across billions of light years. But the spectacle doesn't end there. Often, along the black hole's rotational axis, powerful magnetic fields can funnel some of the infalling material away, launching twin jets of charged particles at nearly the speed of light. These jets can stretch for thousands of light years into space, acting like colossal searchlights that further announce the black hole's presence. It is this entire package, the brilliant accretion disk and the potentially accompanying jets, that transforms an invisible gravitational trap into the most powerful lighthouse in the universe. By training our most sensitive telescopes on these points of extreme brilliance, we are essentially studying the shadow of the black hole, illuminated by the very material it is consuming. This light is then broken down into a spectrum, a rainbow of colors that holds a wealth of information. Specific elements in the swirling gas, like hydrogen or helium, leave unique fingerprints or absorption lines on this spectrum. And here is the real key to measuring distance. Because the universe is expanding, the light from these distant quasars is stretched as it travels through the stretching fabric of space. This stretching causes the entire spectrum to shift toward the red end, a phenomenon known as redshift. The greater the redshift, the farther the light has traveled, and the farther back in time we are looking. So, while we never see the black hole itself, we see its brilliant, energetic dinner plate and use the stretched light from that dinner plate to calculate exactly how old and how far away this cosmic feast truly is. Even with our most powerful telescopes, the light from these most distant quasars is often incredibly faint, a whisper on the edge of detection. So how do we push our vision even further? Nature itself provides a solution, one predicted by Einstein over a century ago. His theory of general relativity revealed that gravity isn't just a force, it's a warping of the fabric of space and time itself. A massive object, like a galaxy or a cluster of galaxies, creates a deep well in this space-time fabric. And just as a glass lens bends light, this gravitational well can bend and distort the path of light rays passing near it. This phenomenon is called gravitational lensing, and for astronomers hunting the earliest black holes, it's an invaluable gift. When a massive galaxy cluster sits perfectly between us and a far more distant quasar, the cluster's immense gravity acts as a natural cosmic telescope. It can magnify the faint light of the background quasar, making it appear dozens of times brighter than it otherwise would. But the effect is often even more dramatic than simple magnification. Instead of seeing one clear image of the quasar, we might see multiple distorted copies of it, stretched into luminous arcs or arranged in a perfect circle around the foreground cluster, known as an Einstein ring. Each of these arcs is a mirage, a different path that the quasar's light has taken around the gravitational well, all converging at our telescopes. A stunning example of this cosmic assistance is a lensed quasar system that appears to be a perfect cross in the sky. This object, sometimes called the Einstein cross, consists of 4 distinct images of the same distant quasar arranged symmetrically around a closer galaxy. Without the gravitational lensing effect of that foreground galaxy, the quasar would be far too faint to study in detail. But thanks to this natural telescope, we can analyze its light spectrum with incredible precision, allowing us to confirm its immense distance and learn about the conditions around its central black hole. Gravitational lensing doesn't just make faint things brighter, it can also reveal details that would otherwise be completely invisible. By studying the subtle distortions in these cosmic mirages, astronomers can even map the distribution of dark matter within the lensing galaxy cluster, the invisible scaffolding that makes up most of its mass. So, every time we observe a beautifully distorted Einstein ring or a multiple image quasar, we are witnessing a double discovery. We're learning about the distant black hole whose light has been magnified, and we're simultaneously probing the mysterious, unseen mass of the closer object that did the magnifying. It's a perfect example of cosmic synergy where one mystery helps to unravel another. This incredible ability to use light as a time machine is perhaps the most profound tool in an astronomer's kit. When we detect the light from one of these distant quasars, we are not just measuring an unfathomable distance. We are opening a window directly into a specific chapter of the universe's history. Think of it as finding a perfectly preserved fossil, but instead of telling us about a single ancient creature, it reveals the entire environment of a lost world. These black holes are our fossils from the cosmos's infancy, and by studying them, we can piece together the conditions of the early universe in a way that would otherwise be impossible. The era we are glimpsing is one of dramatic transformation. Immediately after the Big Bang, the universe was a hot, dense, opaque fog of plasma, a soup of particles and energy where light could not travel freely. After about 380,000 years, it had expanded and cooled enough for electrons and protons to combine into neutral hydrogen atoms, allowing the first light to finally stream across the cosmos. This is the light we see today as the cosmic microwave background. But then, the universe entered a period known as the Dark Ages. It was a profoundly quiet and dark time. There were no stars, no galaxies, and no sources of light beyond the fading glow of the background radiation. The cosmos was filled with vast clouds of neutral hydrogen gas, sitting in darkness for millions of years. The end of this dark epoch is precisely what the light from the most distant quasars helps us investigate. These black holes became active during a period called the epoch of reionization. The intense ultraviolet radiation blazing from their accretion disks began to blast apart the neutral hydrogen atoms that filled the universe, reionizing them back into a plasma of free electrons and protons. This was the final major phase transition of the cosmos, the moment the universe became transparent and filled with light once again. By analyzing the spectrum of a quasar like J0313-1806, astronomers can see the specific fingerprints of this process. The light shows patches where the hydrogen gas has been eaten away, creating bubbles of ionized material. Studying the size and distribution of these bubbles tells us how quickly reionization occurred and what the primary sources of this transformative energy were. Were it solely the first population of stars, or did these early supermassive black holes play a dominant, even decisive, role in lighting up the cosmos? Each distant quasar we discover provides another crucial data point in this cosmic detective story. Furthermore, the environment around these ancient black holes was unlike anything in the modern universe. The cosmos was significantly smaller and denser, meaning galactic collisions and interactions were far more frequent and violent. This constant chaos would have funneled vast amounts of gas and dust toward the central black holes of nascent galaxies, creating the perfect conditions for rapid growth and incredibly bright quasar activity. By studying the properties of these early quasars, their mass, their brightness, the composition of the gas around them, we are essentially taking a core sample of the early universe. We learn about the abundance of heavy elements that could only have been forged in the first generations of stars and then scattered by supernova explosions, seeding the cosmos with the building blocks for planets and life. The presence of dust around some of these very early black holes, for instance, tells us that the first stars must have lived and died incredibly quickly to have produced and distributed these solid materials so soon after the Big Bang. Every piece of information gleaned from their light helps us refine our models of cosmic evolution, turning a theoretical timeline into an observed history. These black holes are not just isolated monsters, they are anchors in time, allowing us to chart the universe's journey from a simple, hot, dense state to the complex, structured, and luminous cosmos we inhabit today. This brings us directly to one of the most profound and persistent mysteries in modern cosmology, a puzzle so challenging it has astronomers rethinking the fundamental pathways of cosmic evolution. We call it the supermassive black hole size problem. On the surface, the timeline just doesn't add up. We have clear evidence of black holes weighing over 1 billion suns, shining brightly when the universe was less than 1 billion years old. But if we follow our standard models, these behemoths should have started from much humbler beginnings. The most logical seed for a black hole is the collapsed core of a massive star. A stellar mass black hole may be 20 or 40 times the mass of our Sun. From that point, it grows by steadily consuming gas and by merging with other black holes. However, there's a speed limit to this process, known as the Eddington limit. This is the maximum rate at which a black hole can pull in material before the intense radiation pressure from its own hot accretion disk actually pushes surrounding gas away, effectively turning off its own food supply. Growing at this maximum theoretical rate for the entire age of the universe still falls short of producing a billion solar mass giant in less than 1 billion years. It's like trying to grow a giant sequoia tree from a seed overnight. The natural processes simply don't operate fast enough to make it possible. So the existence of these ancient quasars presents a stark either-or scenario. Either our understanding of black hole growth is incomplete, or their starting points were radically different from anything we see forming today. This is where a compelling and somewhat terrifying theory enters the picture: direct collapse black holes. Imagine a scenario that bypasses stars entirely. In the dense, pristine environment of the very early universe, before the first heavy elements existed, vast clouds of pure hydrogen and helium gas could have begun to collapse under their own gravity. Normally, such a cloud would fragment into countless smaller clumps, each giving birth to a star, but under very specific conditions, perhaps bathed in the intense ultraviolet light from a nearby massive galaxy's formation, this fragmentation could be suppressed. Instead of shattering into stars, the entire gigantic cloud, weighing tens of thousands of solar masses, would collapse directly into a single monstrous object. There would be no supernova, no brilliant stellar life, just a silent, catastrophic gravitational failure, resulting in the instantaneous birth of a supermassive black hole seed. This is not a small stellar remnant. It's a ready-made supermassive infant, a head start of epic proportions. With a seed that massive, growing to 1 billion suns within a few 100 million years becomes a much more feasible task, even while obeying the physical limits of accretion. The hunt for evidence of these direct collapse seeds is a major focus of next-generation observatories like the James Webb Space Telescope. Astronomers are searching for objects that are incredibly massive and compact but lack the signatures of stellar nurseries, hoping to catch a glimpse of these primordial giants in the act of formation. They represent a missing link in cosmic history, a potential solution to the size problem that rewrites the opening chapter of how structure emerged in our universe. While these ancient black holes exist in the perfect vacuum of space where sound waves cannot travel, they are anything but silent. They broadcast their violent existence across the entire electromagnetic spectrum, screaming their presence through energetic radiation that our instruments can readily translate. Think of it not as sound you could hear with your ears, but as a cosmic symphony of light, with each wavelength representing a different instrument in the orchestra. The serene, visible light that our eyes perceive is just one quiet melody in a much louder and more chaotic performance. The true power of these distant quasars is revealed in the high-energy registers of this symphony, in X-rays and gamma rays. The accretion disk around a supermassive black hole is a crucible of extreme physics where temperatures soar to millions of degrees. Matter this hot doesn't just glow with visible light, it shines brilliantly in X-rays. By deploying space-based observatories like NASA's Chandra X-ray Observatory, we can tune our receivers to this high-energy channel. When we point Chandra at a distant quasar, we don't see a pretty picture in the way Hubble might. Instead, we detect the precise energy signature of this searing radiation, confirming the presence of an intensely active black hole and allowing us to measure its ferocious appetite. Gamma rays, even more energetic than X-rays, can also be produced in the relativistic jets shot out from the poles of these black holes, providing another loud and clear signal of their incredible power. But simply detecting this radiation is only the first step. The real scientific goldmine comes from analyzing it in exquisite detail through a technique called spectroscopy. When the light from a quasar passes through a spectrometer, it is spread out into its constituent colors, creating a spectrum that looks much like a rainbow. However, this rainbow is far from perfect. It is marked by a complex pattern of bright emission lines and dark absorption lines. These lines are the unique fingerprints of chemical elements. Every element in the universe, like hydrogen, helium, carbon, or iron, absorbs and emits light at very specific wavelengths. When we see a dark line in the quasar spectrum at a wavelength characteristic of iron, for example, we know that clouds of iron gas must be present in the path between the black hole and us. This allows astronomers to perform remote cosmic chemistry, determining the exact composition of the material whirling around the black hole and falling to its doom. This analysis reveals something astonishing about even the most ancient black holes. Their surroundings are already enriched with heavy elements. The presence of elements like carbon, oxygen, and iron around a black hole that existed when the universe was only a few 100 million years old is a crucial clue. These elements are not primordial. They were not created in the Big Bang, which produced almost exclusively hydrogen and helium. Heavy elements are forged in the nuclear furnaces of stars and scattered across space by supernova explosions. Therefore, detecting them so early in cosmic history tells us that entire generations of massive stars must have already lived and died, seeding their galaxies with the raw materials for planets and life, all before this distant black hole even reached its brilliant peak. The spectrum does more than just a chemical inventory. It also acts as a probe for the extreme conditions near the event horizon. The light emitted from the inner regions of the accretion disk is subject to immense gravitational forces and velocities approaching the speed of light. These effects cause the spectral lines to be broadened and shifted in ways predicted by Einstein's theory of general relativity. By measuring the precise shape and shift of these lines, scientists can effectively map the mind-bending physics at the edge of the abyss, estimating how fast the disk is spinning and how deeply the black hole's gravity warps the very space around it. So, from a simple pattern of lines in a rainbow of light, we can decode the composition of ancient cosmic material, uncover the history of the first stars, and test the fundamental laws of physics under the most extreme conditions imaginable. Now, let's talk about the sheer, staggering consumption rate that powers these distant monsters. For a quasar to blaze with the brilliance of 1 trillion stars, it requires a constant, colossal inflow of fuel. We're not talking about a leisurely meal. This is a continuous, violent feast of cosmic proportions. The feeding rates of these supermassive black holes are so immense that they defy easy comprehension. Astronomers estimate that to sustain its luminosity, a typical distant quasar must devour an amount of gas and dust equivalent to the mass of our Sun every few days, sometimes even every single day. Just sit with that for a moment. Our Sun is a colossal sphere of incandescent plasma, weighing in at 2 octillion tons. That's a 2 followed by 27 zeros. To consume an object of that scale, to tear it apart and pull it into an accretion disk in such a short time frame, represents a level of destructive power that is almost beyond imagination. It's the equivalent of our entire solar system's central star being swallowed whole, over and over again, in a relentless cycle. This voracious appetite is directly linked to the quasar's unbelievable brightness through one of the most efficient energy conversion processes in the universe, gravitational accretion. As this vast amount of material spirals inward, drawn by the black hole's irresistible pull, it picks up tremendous speed. the gas and dust in the inner regions of the accretion disk rub against each other at velocities approaching the speed of light, creating unimaginable friction. This friction heats the material to temperatures of millions of degrees, causing it to glow with intense radiation across the entire spectrum, from infrared to visible light to X-rays. But here's the critical part. This process converts matter into energy with an efficiency that dwarfs humanity's most powerful reactions. While our nuclear fusion reactors, or even the hydrogen bombs, convert only about 0.7% of mass into energy, the accretion onto a black hole can achieve an efficiency of up to 10% or even more. This means that for every 10 suns worth of material that falls in, the equivalent of one entire sun is transformed into pure, radiant energy. This is the engine that allows a single object, no larger than our solar system, to outshine the combined light of every one of the hundreds of billions of stars in its host galaxy by a factor of 1,000. The galaxy itself becomes a faint peripheral glow, a mere backdrop to the brilliant central beacon. To grasp this imbalance of power, picture a single, dazzlingly bright lighthouse situated in the middle of a vast, dark ocean at night. The lighthouse is so intensely luminous that its beam is visible from hundreds of miles away, completely dominating the seascape. The ocean itself, which represents the host galaxy with its countless stars, is rendered almost invisible by comparison. The quasar is that lighthouse, and its energy output is so concentrated and prodigious that it temporarily overpowers the collective starlight of an entire island universe. This is why quasars were so puzzling to astronomers when first discovered in the 1950s and 60s. They appeared as star-like points of light, but their spectra revealed they were impossibly distant and impossibly powerful. We now understand we were witnessing the active, feeding phase of a supermassive black hole, a transient but spectacular period in a galaxy's life where its central engine is operating at full throttle. This phase cannot last forever, of course. Eventually, the black hole will consume most of the available fuel in its immediate vicinity, or the intense radiation pressure from its own accretion will blow away the remaining gas, temporarily shutting off its food supply. The quasar then fades, leaving behind a quieter but still supermassive black hole like the one at the center of our own Milky Way. But for that brief cosmic moment, it is the undisputed titan of its realm, a devourer of suns whose hunger lights up the early universe. And as we marvel at the insatiable appetite of the central black hole, we must remember that it doesn't exist in a vacuum. It is the heart of a vast, chaotic, and rapidly evolving system, a galaxy in its earliest, most tumultuous stages of construction. The host galaxies of these distant quasars are not the serene, majestic spirals or smooth ellipticals we see in the local universe today. They are cosmic infants, more like frenetic, sprawling construction sites than finished celestial cities. Imagine a scene of incredible chaos and potential. Vast, irregular clouds of pristine hydrogen and helium gas, the raw material of the universe, swirling in immense, turbulent reservoirs. Within these clouds, the first generations of stars are igniting at a ferocious rate, blazing brilliant but short lives before exploding as supernova, scattering newly forged heavy elements back into the chaos. This environment is a far cry from the relatively quiet and orderly Milky Way. It is a crucible of creation, dense, violent, and filled with the energetic feedback of both stellar birth and stellar death. It is within this primordial maelstrom that we find one of the most important and still unfolding revelations in modern astrophysics, the concept of co-evolution. The supermassive black hole at the galaxy's center and the galaxy itself are not independent entities. They are locked in a complex symbiotic dance, each dramatically influencing the growth and destiny of the other. For a long time, astronomers viewed galaxies and their central black holes as separate components, but observations, particularly of nearby galaxies, revealed a startling correlation. The mass of the central black hole is closely tied to the properties of the galaxy's bulge, the dense central cluster of stars. This correlation suggests a profound connection, a shared history of growth. In the dense, gas-rich environments of the early universe, this relationship was likely even more intimate and intense. As the young galaxy formed, gravitational interactions and frequent mergers between smaller protogalaxies would have funneled enormous amounts of gas directly toward the center. This provided a nearly limitless buffet for the nascent black hole, allowing it to rapidly accrete mass and shine as a brilliant quasar. The quasar, in turn, did not just passively consume, it gave back. The incredible energy released by its accretion process acted as a powerful form of cosmic feedback. The intense radiation and powerful jets blasting from the black hole could heat the surrounding gas or even push it entirely out of the galaxy's central regions. This feedback had a dual effect. Initially, it could actually stifle star formation in the immediate vicinity by blowing away the very gas clouds that stars need to form. But on a larger scale, as these energetic outflows traveled outward, they could also compress distant gas clouds, triggering new waves of star formation in the galaxy's outskirts. So the black hole, in its furious feeding, was not just a passive resident. It was an active architect, helping to regulate the pace of construction and ultimately shaping the final structure of the galaxy that hosted it. This dynamic interplay is a key piece of the puzzle for understanding how the most massive galaxies we see today came to be. The brilliant quasars we observe from the early universe are likely snapshots of this brief, hyperactive phase of co-evolution, a period when both the black hole and its host galaxy were growing at an explosive rate. The galaxy provided the fuel, and the black hole provided the energetic engine that helped sculpt the final product. This cosmic dance suggests that the evolution of a galaxy and the growth of its central black hole are two sides of the same coin, a deeply interconnected process that began in the chaos of the early cosmos and set the stage for the diverse galactic population we observe billions of years later. This brings us to the very heart of the mystery. If a baby stellar black hole is too small a seed, what kind of seed could possibly grow into a billion solar mass giant in less than a billion years? Astronomers are exploring several fascinating pathways, but two leading hypotheses stand out, each painting a very different picture of the universe's first moments of structure. The first theory points to the very first stars to ever ignite in the cosmos, known as population 3 stars. These weren't your average stars, they were behemoths, true cosmic titans. Born from clouds of pure hydrogen and helium with no heavy elements to help them cool and fragment, these stars could have grown to staggering sizes, some potentially reaching several hundred times the mass of our Sun. Their lives were brilliant but incredibly short, burning through their nuclear fuel in just a few million years before collapsing in spectacular supernova known as pair instability explosions, which would have blown them to smithereens, leaving behind no remnant, or in some cases, collapsing directly into black holes of perhaps a few hundred solar masses. A seed of a few hundred suns is certainly a much better starting point than a single stellar corpse. It's like starting a farm with a team of oxen instead of a single horse. You can plow the fields much faster. However, while this is a compelling idea, many simulations still struggle to get these population 3 remnant seeds to grow fast enough to explain the very earliest supermassive black holes we see. The race against the cosmic clock is simply too tight. This is why many scientists are increasingly drawn to a more dramatic, almost apocalyptic scenario, the direct collapse model. Imagine bypassing stars entirely. In the dense, dark environments of the early universe, vast primordial gas clouds, weighing tens of thousands or even hundreds of thousands of solar masses, could have begun to collapse under their own weight. Normally, such a cloud would naturally fragment into thousands of smaller clumps, each forming a star. But under very specific and rare conditions, this fragmentation could be prevented. One key ingredient is a powerful source of external ultraviolet light. If a nearby early galaxy was forming its first stars, its intense UV radiation could blast the gas cloud, keeping the hydrogen atoms from pairing up into molecules. Hydrogen molecules are very efficient at cooling gas, and cool gas is more likely to condense and fragment. Without this efficient cooling mechanism, the vast cloud cannot break apart. It simply continues to collapse, a monolithic, silent, and catastrophic gravitational failure. There is no nuclear fusion, no brilliant stellar birth. The entire colossal cloud plummets directly into a single point, giving birth to a black hole seed of immense proportions, not a few hundred solar masses, but a ready-made monster of 10,000, 50,000, even 100,000 suns right from the start. This is the ultimate head start. With a seed this massive, the growth to 1 billion solar masses becomes a much more manageable feat, even within the constraints of the Eddington limit. It's the difference between trying to grow a giant redwood from a tiny seed versus planting a substantial sapling. The path to a giant is far quicker and more direct. The direct collapse model is particularly favored for explaining the very earliest and most massive quasars because it provides the necessary jump start. It also predicts a unique signature that next-generation telescopes like the James Webb Space Telescope are actively searching for. An object that is incredibly massive and bright in infrared light, but shows no signs of the heavy elements that are always produced by stars. Finding such an object, a massive, compact, yet chemically pristine beacon, would be the smoking gun evidence for a direct collapse black hole seed caught in the act of formation. While the conditions for direct collapse were likely rare, in a universe as vast as ours, even rare events will happen, and it may only take a handful of these super seeds to explain the population of supermassive black holes that came to dominate the cosmic landscape. These two theories represent the frontier of our understanding, a debate that takes us back to the very first structures that ever condensed out of the cooling embers of the Big Bang. So we have these two competing ideas for how a supermassive black hole seed might form, but that only addresses the starting point. The next great challenge is understanding the engine of growth itself. How do you take even a massive seed and make it 1 billion times larger in a cosmic blink of an eye? This brings us to a fundamental law of physics that acts like a cosmic speed governor for black holes, a concept known as the Eddington limit. Named after the renowned astrophysicist Sir Arthur Eddington, this principle defines a delicate balance, a point of equilibrium between two opposing forces. On one hand, you have the immense gravitational pull of the black hole, relentlessly dragging gas and dust inward. On the other hand, as that material is compressed and heated in the accretion disk, it emits an incredible amount of radiation. This radiation exerts an outward pressure, much like a strong wind pushing against an object trying to move through it. The Eddington limit is the precise point where these two forces cancel each other out. If a black hole tries to consume matter any faster than this limit, the radiation pressure from its own feasting becomes so intense that it literally blows away the surrounding gas cloud, shutting off its own food supply. Think of it like trying to light a campfire in a hurricane. The stronger the fire burns, the more wind it creates to blow itself out. For a typical black hole growing at a steady, sustainable pace, this limit acts as a natural brake, preventing it from growing too quickly. Astronomers can calculate this maximum rate, and it translates to a black hole roughly doubling its mass every 50 million years or so. Now do the math for the early universe. If 100 solar mass seed from a population 3 star started growing right after the Big Bang and stuck strictly to the Eddington limit, it would still fall far short of reaching 1 billion solar masses by the time we see quasars like J0313-1806. The numbers simply don't add up. This glaring discrepancy is what forces astronomers to consider a much more violent and unstable mode of feeding: super Eddington accretion. This is the hypothesis that the earliest black holes didn't play by the polite rules of equilibrium. They gorged themselves in feeding frenzies that shattered the supposed speed limit. But how could they possibly exceed this fundamental limit? The key likely lies in the unique, chaotic environment of the infant cosmos. Our standard model of a smooth, spherical accretion disk might not apply. Instead, imagine the inflow of gas is highly uneven and clumpy. Dense, massive clouds of material could fall directly toward the black hole, somewhat shielded from the intense radiation blasting out from the poles or the inner disk. It's a scenario akin to a freight train pushing through a gale force wind. If the train is heavy and dense enough, it can overcome the resistance. In this super Eddington state, the accretion disk would become incredibly thick and puffy, a bloated and turbulent torus of gas. The radiation, struggling to escape through this dense shroud, would actually push material into the black hole in some regions even as it blows other material away. This process would be spectacularly messy and inefficient in converting mass to energy, but it would allow for a much higher rate of mass consumption. The black hole would be eating like a glutton, not a gourmet, spilling a lot of its food but still packing on mass at an incredible rate. Evidence for such extreme behavior is beginning to emerge from observations of some distant quasars and from computer simulations. Some quasars show brightness fluctuations that are far more violent and rapid than what a stable, Eddington-limited disk would produce, hinting at these chaotic feeding episodes. Furthermore, the powerful outflows and jets we see associated with many early quasars are a direct signature of the immense radiation pressure that characterizes super-Eddington accretion. These outflows are the universe's way of balancing the books, the violent exhaust from an engine operating way beyond its red line. So, while the Eddington limit remains a crucial rule of physics, it seems the early universe provided special conditions where this rule could be bent, if not entirely broken, allowing nature to build its most magnificent monsters on a deadline. And that super Eddington feeding frenzy we just discussed has a direct and dramatic consequence, one that reshapes the entire galaxy: the generation of immensely powerful black hole winds. These are not gentle breezes, they are hurricanes of energy, vast outflows of material that are blasted away from the accretion disk at velocities that can reach a significant fraction of the speed of light. Think of it as the ultimate cosmic exhaust system. As the black hole gorges itself, the incredible radiation pressure and intense magnetic fields generated in the maelstrom don't just heat the incoming gas, they actively propel a portion of it back out into space. This creates a feedback loop of astonishing power. Some of these winds are relatively narrow, focused jets shooting out along the black hole's rotational axis. But others are much broader, a more spherical blast that pushes outward in all directions, like a shock wave from a continuous explosion. The importance of these winds cannot be overstated, as they play a dual role in cosmic evolution. First, they act as a built-in regulator for the black hole's own growth. By violently expelling the very gas that serves as its fuel, the wind effectively turns down the thermostat on the quasar's engine. This self-regulation prevents the black hole from growing completely out of control and likely contributes to the relatively short, brilliant lifetime of the quasar phase. But the second, and perhaps more profound, effect is on the host galaxy itself. These winds carry an immense amount of energy out into the galactic environment. As they sweep through the galaxy, they heat the vast reservoirs of cold, dense gas, the exact raw material needed to form new stars. This process, known as quenching, effectively sterilizes the galaxy's central regions. By heating the gas, the winds prevent it from cooling, collapsing, and igniting into new stars. It's a dramatic case of the central black hole shaping the destiny of its entire home. A galaxy that might have been destined to form stars for billions of years can have its future star formation sharply curtailed by a particularly energetic outburst from its core. This feedback mechanism is a cornerstone of our understanding of why massive elliptical galaxies, which often host the largest black holes, have so few young stars today. Their star-forming gas was likely heated and expelled eons ago by the powerful winds from their brilliant quasars. So, these outflows are not just a side effect of a feeding black hole. They are a fundamental force in galactic construction, a key piece of the puzzle in how the universe transitioned from an era of chaotic, rapid star birth to the more orderly and quiescent galaxies we see around us today. To truly understand the significance of these distant black holes, we need to pull back from the individual galaxy and view the cosmos on its grandest scale. They are not isolated monsters floating in a random void. They are strategically positioned at the most powerful and dense locations within the universe's largest structure, an immense architecture known as the cosmic web. Imagine the universe not as a scattered collection of islands, but as a single, vast metropolis. In this cosmic city, galaxies are the buildings, and the supermassive black holes at their centers are the powerful engines housed within the most important skyscrapers. But what dictates where these skyscrapers are built? The blueprint for this entire metropolis is written in dark matter. This invisible, mysterious substance, which makes up about 85% of all the matter in the universe, does not interact with light, but its gravitational pull is the dominant force shaping the cosmos. After the Big Bang, tiny fluctuations in the density of dark matter were amplified by gravity over billions of years. Regions that were slightly denser than others began to pull in more and more material. This process woven the dark matter into an enormous web-like network of filaments, vast threads that stretch across the emptiness of space, connecting at dense hubs or nodes. This is the cosmic web, the hidden scaffolding upon which all visible structures are hung. The ordinary matter, the gas and dust that make up stars and planets, simply followed the gravitational roadmap laid down by the dark matter. It flowed along these invisible filaments, funneling into the intersections where multiple filaments met. These nodes became the sites of incredible activity, the downtown centers of the cosmic city where the raw materials of the universe converged. It is at these bustling intersections that the first and largest galaxies were destined to form. And at the heart of these primeval mega-galaxies, the conditions were perfect for nurturing supermassive black holes. The constant influx of gas from multiple filamentary highways provided a limitless fuel supply, allowing the central black hole to feast at a ferocious rate and shine as a brilliant quasar. So, when we detect one of these incredibly distant early quasars, we are almost certainly pinpointing a major nexus in the infant cosmic web. We are finding a location where the tides of dark matter and gas conspired to create a cosmic powerhouse. This explains why these objects are so exceptionally massive so early on. They had a gravitational head start, forming in the deepest potential wells the young universe had to offer. Their brilliance is a beacon that illuminates not just themselves, but the entire underlying structure of the cosmos, highlighting the dense knots in the web that would eventually evolve into the massive galaxy clusters we observe today. Determining the mass of a black hole here in our cosmic neighborhood is challenging enough, but doing it for a monster 13 billion light-years away seems almost like a magic trick. How can we possibly weigh an object we can't even see, at a distance where its light is a faint whisper? The answer lies in a brilliantly clever technique that turns the black hole's own violent flickering into a cosmic scale. This method is known as reverberation mapping, and it relies on the fundamental principle that the immense gravity of the black hole dictates the speed at which things orbit around it. To understand how it works, picture the environment around an active supermassive black hole. At the very center is the event horizon, the point of no return. Just outside that is the intensely bright accretion disk, a flat, swirling pan of superheated gas. Farther out, surrounding the entire system, is a large, diffuse cloud of slightly cooler gas known as the broadline region. This cloud is not a calm, placid thing. It's a frenzied maelstrom of gas clouds orbiting the black hole at tremendous speeds, thousands of kilometers per second. Now the accretion disk doesn't shine with a steady, constant light. It flickers and flares unpredictably, its brightness changing over days, weeks, or months. When a particularly bright flare erupts in the inner accretion disk, it sends a pulse of high-energy ultraviolet light radiating outward in all directions. This flash of light is like turning on a lighthouse beacon for a brief moment. That flash of light takes a certain amount of time to travel outwards to the broad line region. When the light finally reaches the gas clouds in that region, it energizes them, causing them to glow with their own specific light, which we can see as emission lines in the quasar's spectrum. The key measurement is the time delay between the initial flare in the accretion disk and the responding flare in the broad line region. Since we know the speed of light is constant, this time delay directly gives us the distance between the accretion disk and the broad line region. It's essentially a cosmic echo, like shouting in a canyon and measuring how long it takes to hear the echo to determine the canyon size. Once astronomers have measured that radius, they can then use the simple laws of orbital mechanics, the same laws that tell us how fast planets orbit the Sun. The speed of an object in a stable orbit is determined by the mass of the central object it's orbiting. By measuring the velocity of the gas clouds in the broad line region, which we can do by looking at how broadened their spectral emission lines are, and knowing the size of the region from the reverberation delay, we can directly calculate the mass of the central black hole. It's a beautiful, indirect piece of detective work. We don't see the black hole, we see the frantic dance of the gas it holds captive, and from the tempo and scale of that dance, we can deduce the mass of the invisible dancer at the center. Applying this technique to the light from distant quasars, which has traveled for billions of years, allows us to place these ancient leviathans on a scale, confirming their astonishing billion solar mass sizes and solidifying the profound mystery of their rapid growth. But what mechanisms could possibly deliver such a colossal and continuous supply of fuel to these cosmic engines? The answer lies in one of the most dramatic and common events in the early universe, galaxy mergers. In the infant cosmos, galaxies were much closer together than they are today, and the universe was a far more chaotic and violent place. Frequent, high-speed collisions between young, gas-rich galaxies were not the exception, they were the rule. These weren't the slow, graceful dances we sometimes see in the local universe. They were catastrophic pile-ups that fundamentally reshaped the galaxies involved. When two such galaxies collide, their stars typically pass right by each other, like swarms of bees merging, because the spaces between stars are so vast. But their immense clouds of interstellar gas are a different story. During a merger, these gaseous reservoirs slam into each other, creating tremendous shock waves that compress the gas and trigger furious bursts of star formation. More importantly for our story, the chaotic gravitational forces during the collision act like a giant spoon stirring a cosmic pot, disrupting the orderly orbits of gas clouds and flinging vast amounts of material inward, directly toward the galactic centers. This process is the ultimate fuel delivery service for a hungry black hole. Simulations of these galactic collisions show gorgeous, intricate tidal tales of stars and gas being pulled out into space, while deep within the merging core, a frenzy of activity takes place. As the two galaxies' central black holes spiral toward each other, the gas that has been funneled to the center forms a thick, turbulent shroud around them. This provides a feast of epic proportions, allowing the black holes to enter a phase of super-Eddington accretion, rapidly packing on mass and igniting as brilliant quasars. The merger essentially turns a placid, star-forming galaxy into a furious quasar, a beacon of light that can be seen across the universe. This intimate link between collisions and quasar activity is a cornerstone of our understanding of black hole growth. It explains why quasars were so much more common in the early universe, because mergers were happening all the time. It also provides a natural explanation for how enough gas could be directed to the center fast enough to build a billion solar mass giant. A single major merger could provide enough fuel to power a quasar for tens of millions of years. For the most massive black holes we see at high redshifts, they may have been the beneficiaries of multiple such mergers, a series of cosmic banquets that allowed them to grow to such immense sizes on a relatively short cosmic timescale. This incredible power output connects these distant quasars to one of the most important turning points in cosmic history, the end of the universe's dark ages. For hundreds of millions of years after the Big Bang's initial flash faded into the cosmic microwave background, the cosmos was a profoundly dark and simple place. It was filled with a pervasive fog of neutral hydrogen gas through which light could not travel freely. The first stars and galaxies were only just beginning to flicker on, their light too feeble to pierce the gloom on a universal scale. The brilliant ignition of the first quasars changed everything. They acted as the universe's first great beacons, and their intense ultraviolet radiation began to fundamentally alter the very fabric of space. This high-energy light was powerful enough to blast apart the neutral hydrogen atoms, stripping away their electrons and reionizing the gas back into a plasma. This monumental transformation, known as the epoch of reionization, was the final major phase change of the cosmos, the moment the universe became transparent and filled with light once again. We can actually see the evidence of this process in the light of the quasars themselves. When astronomers analyze the spectrum of a quasar like J0313-1806, they don't see a perfect continuous rainbow. Instead, they see a pattern of dark absorption lines, often referred to as the Lyman alpha forest. These lines are created as the quasar's light travels through billions of light years of intergalactic hydrogen gas on its journey to us. Each dark line corresponds to a specific cloud of neutral hydrogen that has absorbed a tiny fraction of the quasar's light at a particular wavelength. The remarkable thing is that for quasars at a certain distance, corresponding to a time when the universe was around 1 billion years old, this forest of absorption lines suddenly disappears. It's as if a cosmic fog has lifted. This tells us that by that time, the collective ultraviolet radiation from the first stars, galaxies, and especially these brilliant quasars had done their work. They had ionized the vast majority of the hydrogen in the universe, clearing the fog and making the cosmos transparent. These distant black holes were not just passive residents of the early universe. They were active participants in its construction, wielding their incredible energy to sculpt the very medium through which light travels, ultimately determining what we can see today. But while quasars are the brilliant, screaming headlines from the early universe, they only tell part of the story. For every one of these dazzling, actively feeding behemoths, there were likely countless others that were silent, lurking in the darkness. These are the dormant giants, the quiescent supermassive black holes of the early cosmos. Imagine a sleeping dragon versus one breathing fire. Both are equally massive and powerful, but one is far, far harder to spot. A quasar's incredible brightness comes from its accretion disk, the blazing whirlpool of material it is actively consuming. But if that flow of gas is cut off, perhaps because the black hole has blown away its immediate fuel supply with powerful winds, or because a merger has not recently funneled fresh material its way, the disk fades. The brilliant beacon winks out and the black hole returns to its natural state, a gravitational pit of pure darkness emitting nothing. It still possesses its immense mass and gravity, but without a glowing dinner plate, it becomes nearly invisible against the vast blackness of space. Detecting these dark giants is one of the most formidable challenges in modern astronomy. Without the brilliant light of a quasar to guide us, how do we find an object that emits no light of its own? The answer lies in observing their gravitational influence on their surroundings. Even when dormant, a supermassive black hole's gravity dominates the center of its host galaxy. Stars very close to the center will orbit at tremendous speeds, whipped around by the immense gravitational pull of the unseen mass. By carefully measuring the velocities of these stars using a technique called spectroscopy, astronomers can detect the telltale signature of a massive central object. This method works well for relatively nearby galaxies like our own Milky Way, where we can resolve individual stars. But for a galaxy billions of light years away, the stars are blurred into a single, faint smudge. Picking out the subtle dance of stars around a central black hole at such distances is currently beyond the reach of our telescopes. This is why finding these early dormant black holes is a primary scientific goal for the next generation of observatories, like the James Webb Space Telescope and the upcoming extremely large telescopes on the ground. Their unparalleled sensitivity and resolution will allow us to peer into the hearts of these ancient galaxies and detect the faint gravitational whisper of a sleeping monster. Why is this search so important? Because it completes the census. If we only study the brilliant quasars, we are only looking at the black holes that are currently feasting. This gives us a biased view of their population and growth history. Finding the dormant ones tells us how common these giants really were, how long their active feeding phases lasted, and what they do during their long periods of quiet. It's the difference between trying to understand their behavior by only observing them during salmon season versus also studying them in hibernation. Each dormant black hole we discover adds a crucial missing piece to the puzzle of how these cosmic titans evolved and shaped the galaxies they call home from the very beginning. All of this detective work, peering back to the very first structures, relies on having the right tools for the job. For decades, astronomers have been like detectives trying to solve a cosmic crime with only a flickering candle for light. But now we have a floodlight. The James Webb Space Telescope is not just an incremental upgrade. It is a complete revolution in our ability to explore the cosmos, and its impact on the hunt for the earliest black holes has been nothing short of breathtaking. The key to its power lies in its specialization. It is primarily an infrared observatory. To understand why that is so crucial, remember the concept of redshift. As light from the most distant objects travels across the expanding universe, its wavelengths are stretched. For light that has been traveling for over 13 billion years, this stretching is so extreme that the light which left its source as visible or even ultraviolet radiation arrives at our telescopes as infrared light. It's like a cosmic siren song being shifted down into a register that only specialized ears can hear. Webb's giant golden mirror and incredibly sensitive infrared instruments are those ears, perfectly tuned to catch the faint, stretched whispers from the dawn of time that previous telescopes like Hubble simply could not detect. Furthermore, infrared light has a unique ability to pierce through cosmic dust. The environments where early stars and black holes formed were filled with thick clouds of dust, which block visible light but are largely transparent to longer infrared wavelengths. Webb acts like a pair of night vision goggles, allowing us to see through the obscuring veils and directly observe the nurseries of the first supermassive black holes. Almost immediately after it began operations, Webb started rewriting the textbooks. It has identified a population of galaxies in the very early universe that are surprisingly massive and mature, existing far earlier than our models predicted. And nestled within the hearts of some of these precocious galaxies, astronomers have found the telltale signatures of actively growing black holes. In one spectacular case, Webb detected a black hole in a galaxy named GNZ 11, which existed when the universe was just over 400 million years old. While not yet holding the absolute distance record, the black hole in GNZ 11 presents another staggering puzzle. It appears to be far more massive relative to its host galaxy than the correlations we see in the modern universe. This suggests that in the earliest epochs, black holes might have grown first, with their galaxies catching up later, flipping our understanding of co-evolution on its head. Webb's detailed spectroscopic capabilities are also allowing scientists to perform a kind of remote surgery on these ancient objects. By analyzing the faint infrared spectra of these early quasars, they can measure the composition of the gas around them, the speed of their winds, and the mass of the central black hole with unprecedented precision. Each new observation is a data point that helps constrain the wild theories about how these giants formed so quickly. Is there evidence for heavy elements pointing to rapid star formation before the black hole ignited? Or is the environment more pristine, hinting at a direct collapse origin? Webb's sharp infrared eyes are providing the evidence needed to move beyond speculation and toward answers. It is effectively acting as a time machine, giving us a front-row seat to the epoch of first light, a period we could previously only theorize about. With every deep field image and every spectrum it captures, the James Webb Space Telescope is not just finding new distant black holes. It is illuminating the very pathways of cosmic evolution, revealing the conditions that allowed these gravitational monsters to emerge and dominate the young cosmos.